In this example problem, we have a wave traveling through a string that has a wavelength of 20 centimeters and a frequency of 300 hertz. And we know the length of the string is 0.75 meters and is under a tension of 430 newtons. And we want to know what the mass of the string is. So we have a wave traveling through a string, which means we want to use our equation for a wave traveling through a string. So that's the idea that the velocity equals the square root of the force of tension divided by the linear mass density, where the linear mass density is equal to mass divided by the length of the string. So if we can figure out what the linear mass density is, we can establish what the mass of the string is, because we have the length of the string. In order to find our linear mass density, we already have the force due to tension that was provided in the problem, but we need the velocity of the wave through the string. And we can find that because we have both the wavelength and the frequency. So velocity of a wave equals its frequency times its wavelength. So we take our 300 hertz, and we need to convert the 20 centimeters into meters by dividing by 100. So we get 0.2 meters. So the velocity of the wave is 60 meters per second. So I can plug that in for the velocity, and set that equal to the square root of the 430 newtons divided by the linear mass density. So our linear mass density is going to be 0.119 kilograms per meter. And then we're going to take that linear mass density and multiply it by the length, so 0.119 kilograms per meter times 0.75 meters, to get a mass of 0.09 kilograms.